Um, Let me start by saying a couple of things about my career trajectory. I started off working on my PhD in robotics and motion planning. A couple of things that came out of that was some new path planning algorithms, a new star path planning, and a tool for doing robust optimal mission planning using quantitative measures of formal languages. Not going to go into that. Then it got a little more abstract. It started working in automated decision making. The main paper that came out of that effort was this, how to describe it quickly. It's like a general decision theoretic routing algorithm in ad hoc networks. When I went to Cornell, things got even more abstract. I got interested and started working on unsupervised machine learning. And the papers two important papers that came out of Cornell was this inverse Gillespie algorithm and the algorithm Genesis, which I'm going to talk about a little today. The inverse Gillespie, if you're familiar with the Gillespie stochastic simulation, it's essentially a way of simulating chemical reactions in a detailed mode in a stochastic setting. What the inverse Gillespie does is to go from data to finding those chemical reaction networks. It's kind of quite neat. You can look it up. It got published in PNS. The Genesis, which stands for generator extraction from self-similar semantics, is essentially a way of computing or inferring models without putting anything in the first place, so unsupervised, non-parametric, symbolic model inference. I'm going to talk about that a little bit. And currently, I'm mostly interested. I do quite a few things, but the core interests are essentially unsupervised machine learning, the ways we can infer causation from data, and this idea of universal similarity, which was introduced in this paper on data smashing, which came out last October in Royal Society interface. So let's go into the main idea in this talk. So how does the scientific method work? Everybody knows that here. It's pretty much a loop. You make experiments, get data, make an hypothesis, see if the hypothesis is valid by doing tests, let's get more data, refine the hypothesis if necessary, and when it stops changing, you have a scientific consensus. Now, the way it works is all the automation is used quite a bit nowadays. So mostly the machines do routine tasks in the lower half of the loop, and the real science is done by humans, making sense of data and so on. And that is getting harder and harder. And the main reason for that is, of course, data. For example, astronomers have collected more data in the last 6 months than they have collected in the entire 600-year history of the field. So it's getting even more and more difficult to actually sit down, go through the data, make those connections, make new discoveries. That's harder and harder. It gets harder and harder every day. Even in biology, because of this high throughput experiments, single cell monitoring that's coming up, it's getting there, where it becomes very hard to do those things manually. So we need in some way to automate the upper half, at least in part or in a significant manner. And while automated hypothesis generation efforts do exist, they are not really effective in real problems that much. A general tool which works independent of a particular domain or can be easily modified to work in different domains is still missing. So what I'm talking about here is going from data to explanation in an automated way, machines finding explanations from data. And what is the main problem? What are the challenges? So I think one of the key challenges is this notion of finding good features. So as machine learning stands now, as a state-of-the-art technology, the state-of-the-art of technology is, if you can find good features for a problem, you can pretty much solve it with off-the-shelf tools. The issue, and there are many issues, but take a bird's eye view of it, essentially boils down to finding good features. And that's kind of a conundrum, because the definition of a good feature is one that works. So to a priori find what is a good feature. If you don't know that in the first place, if you don't have experts telling you what the good features are, it's kind of difficult. Now, there is some work which tries to come up with features with deep learning networks, hierarchical construction, and so on. But the question is, or one of the important, interesting questions is, to me, whether we can go around this problem. Can we do something where we do not need to find or specify features? And, well, I think we can. And I think the way to do it is to come up with a rigorous way of thinking about this notion of similarity. Why is that? Because I kind of propose that notion of similarity is foundational to all learning. For example, if you say that some animal is a cat, what you're saying is that this particular animal is similar to all these other animals, which is similar to each other, and the label assigned to them is a cat. And it's different from these other animals, which are also similar to each other, but not similar to these animals, and these are known as dogs or something else. So this notion of similarity is kind of foundational. If you think about modeling a stochastic time series, and you come up with a model, what you're saying is that this abstraction you came up with generates data, which is in some sense, in a clearly defined, rigorous sense, similar to the data you started with. That's what it means to have a model of a stochastic time series. So this notion of similarities is very, very important. The problem is it doesn't really get us anywhere because it's kind of very intuitive notion. It's not clear how we are going to use that or make it rigorous or compute it and so on. Sometimes it's quite easy to see what intuitively easy, right? So in this example, for example, the first three, most of you would agree, are similar, while the thing that stands out, the excerpt, the time series excerpt that stands out is this one. But here, of course, you're kind of mentally picturing difference in frequencies or things like that. Can we have like a more universal approach to it, where we don't have to specify what is the feature that we are using to find or differentiate between similar objects and dissimilar objects? This is not a problem for deterministic systems. If you're modeling, say, a sine wave, you come up with a model for a sine wave, it's easy to know whether you have the correct model because it produces a sine wave, and that's what you have to verify. Even with noise, it's just a sine wave. The problem is when you have
So I would say that even in deterministic systems, if you have some non-linearity,
yeah.
If you have a chaotic system and you the parameters from integrable and non-integrable.
Well, good. That's great. I was just trying to say some systems this is not relevant. It's just great. So yeah, it's definitely true. A chaotic system where you cannot specify the the initial parameter very precisely, that starts behaving like a stochastic system. You can model it as a stochastic process too. I mean, it's
Not quite, but we can discuss it.
yeah, sure. So the problem where it is clearly relevant, it's also relevant for some deterministic systems, is when it is driven by a stochastic process, because what you see, the finite observations, is a sample path, and you have one sample path, you come back and look at it, it's a different sample path. So the question then boils down to, and this is the problem definition, that if you have this finite sample paths, can we tell from just this whether they've been generated by the same underlying process? And so are they similar? So if you make assumptions on the system, then yeah, this becomes a very simple thing. If you assume they are both, that somehow you know, somebody told you that they're both Gaussian processes, and yeah, you just find the Gaussian parameter. If you know their point, you find parameters and compare them. But if you're willing to entertain the possibility that you don't know what the statistics are or what it could be, then that becomes a problem. How do you compare them without knowing anything with finite data? So that's the issue. What is done, and to give another example, this is what a possible application could be. This is where I want such an algorithm to go or do. If you have, say, 4 samples of brain waves of possibly 1 or more subjects, with just this data, I want this data similarity detection approach to come in and say, well, the first 2 are similar, the second 2 are similar, and they're dissimilar from each other, which corresponds to the fact that they are from 2 different subjects. And that's what I wanted to do. So how is it done in the state of the art? As I said, it depends heavily on finding features. So you take time series data, or it doesn't have to be time series, just ordered data. You map it to a feature space, low-dimensional feature space, and you get feature vectors, and you just compare those feature vectors, find distance between two finite vectors. Now, it is deeply unsatisfying to me. The reason is, first you took a long data stream, mapped it to a 4-dimensional space, 10-dimensional space, so you lose a lot of information. And then you are using these features, which means that somebody came and told you what those features are. So if you want to discover new things, that's a problem. So what if we could do something like this? What if we could treat the information contained in the data stream as a more physical quantity? We can't, but let's just take it forward and think about what would happen if we could. What if we could take a signal, invert it to get an anti-signal, somehow make it interact with the other stream, and if these two came from the same process, so they contain the same kind of information, once you invert it, it has the anti-information. That kind of cancels each other out, and what you get is flat white noise in the output. So if we could do this, then we could just, asking whether the output is noise, flat white noise, you could say whether they are similar, right? Whether they came from the same underlying process. Now, of course, that's kind of wishful thinking at this point, because I didn't tell you what you mean by invert. What does an anti-stream mean for a given signal? What do you mean by interact, and so on? Surely it can't be just negating values. The sequence of ones has exactly the same information as a sequence of minus ones. So it's not that. So what is it? Intuitively, I'll come to a rigorous definition later, but intuitively, given a stream S, and assume it's a binary stream, sequence of zeros and ones, then an anti-stream S prime has to qualify, S prime to qualify as an anti-stream of S, it has to satisfy the following properties. So assume 0 and 1 occur in stream S with 70% and 30% frequency. Then in the anti-stream, it has to be inverted, 30-70. That's not enough. You also have to kind of invert it for length 2 sequences, length 3 sequences, and so on. These are all finite streams, but if S prime keeps satisfying this forever, then that qualifies as an anti-stream for S. So in that sense, the anti-stream has an inverted statistical structure. This is not a rigorous definition, mind you. I'll come to that in a moment. And let's talk about that, actually, how to make it rigorous. Before I go forward, one thing to note here, all data streams that I'm talking about in this talk are quantized. They're essentially streams or sequences of symbols, which means that if you have a continuous valued time series, I am breaking up the range in a finite number of levels, that's the quantization alphabet, and mapping the time series to a symbolic sequence. You have some lots of information there, but I don't want to go into too much details how you can do that. But that's what we are doing. So now, given such a thing, a stochastic process, quantized stochastic process, we're going to make a couple of more assumptions. But note that for any process like that, which generates sequence of symbols, if you specify the next symbol distribution for all histories, any length of history, what is the distribution of producing the next symbol over the quantization alphabet? If you specify that, if you write that down, you can't, it's an infinite table, but if you could, we could write it down, then that specifies the entire system. There's nothing more left to specify. That specifies the dynamical system. Which means that if you add some more assumptions, it's not really necessary to add for this particular point, but if you add them, essentially an ergodic stationary quantized process is described by this probability measure on infinite strings. And that should be obvious intuitively. Of course, you can also make it rigorous. You can come up with a construction of measured space and all that. So that should be obvious.
So let me just put it in physics terms. So you're first matching a one-point function of a process or in level sets, and then you're looking at what correlations in time. Are you using 2-point, 3-point, n-point correlation? Or what's that actual?
Don't go into 1-point, 2-point correlations. Exactly what I said. Nothing to read between the lines. You have a black box producing data, and if you specify, and suppose this is your history, you see. Now, what is the next probability distribution of the next symbol? Now, that may depend on nothing. If it's a Bernoulli half process, depends on nothing. Doesn't matter where you need to see that. It's always half-half. But suppose it has some correlations, long range, depends on history. Now, how long are histories are important? At the worst case, entire history is important. That's what I said. If we write down everything, all the next symbol distributions for all histories.
Practically, we usually don't use all history, right?
No, it's a theoretical construct. It'll become obvious why I said that. But yeah, of course you don't. And if a system does, in fact, depend on infinite histories, you can't really write anything down. That's like incompressible. That is a Kolmogorov random string, but that's for a theoretical construct. That's the worst case scenario. If you could write down that table, there's nothing more to write down, essentially. That's the point. Now, how does this probability measure look like? Let's talk about that a little bit. So the probability space is constructed as follows. The underlying space is sigma omega. Sigma is the quantization alphabet. Sigma omega is a set of strictly infinite strings on the alphabet. And the sigma algebra is the smallest sigma algebra generated by sets which look like this. X sigma omega. X is a finite prefix. You can think of that as a string that has already happened. And sigma omega, again, is a set of all strictly infinite strings on sigma. And mu is just a probability measure, as you would define. It's a finite measure on that space. And countably additive and all that. So this particular probability space, this particular construction has some interesting properties. For example, you can show this probability measure on infinite strings induces a right invariant equivalence relation on finite strings. And that's actually very, very important. Because if you are familiar with the construction, how finite state automata are introduced in Hopcroft-Ullman or the basic thing, then you would know that any right invariant equivalence relation on finite strings necessarily induces a finite automaton. And in this case, the equivalence relation is that two strings, finite strings, are equivalent if any right extension has the same measure. So that means any two strings are equivalent. Doesn't matter which string actually happened in the past, so it defines a state, which means the equivalence classes become states, or as I call them, causal states. Not I, actually. Jim Crushfield called that causal states. But they become states, and essentially this particular construction induces a probabilistic automaton. Things like this. You have states, transitions between them, labeled with alphabets, and transition probabilities. Now, why did I go through that measure construction? I could have just said, here is a probabilistic automaton. And that would have been a valid starting point. The reason is, this allows you to see that this probabilistic automaton are not the fundamental objects. They, in fact, are encodings for this underlying space of measures on infinite strings. And that two PFSAs can encode the same measure, although a unique minimal realization does exist. So that's the point. That means if they look different,
Why do you need an infinite string?
because it cannot stop. That's why. Why does dynamical systems, when you define, or it's potentially infinite. Why do you need any?
Of any math that requires infinity, because most data sets are
Do you use limits in your calculations?
Okay.
Yeah, no, it will not matter here as well. So that's a very interesting question. See, that's what's happening. This is a measure on infinite string, but the measures which are not compressible as finite state automata are not something we can really handle. It actually has to be approximable by a finite state automaton. So this construction before only tells you that there is a finite probabilistic automaton model for this since there's an equivalence relationship. Whether it's finite depends on whether you have a finite number of states. So yeah, this is a measure in infinite strings, but we'll never actually have to worry about that because we can only worry about this space of PFSAs, which is a finite encoding of something like an infinite object. So that's fine. Yeah, if you have to manipulate infinite objects, that would be a problem. So does that answer your question? Okay. So what's a good thing? Why do I even worry about this space? Because it's easier to do math there and make proofs there that we are going to apply in the higher space. For example, the space of measures, it's very easy to define a closed binary operation on them. So given two measures, P1 and P2, we can define P3 essentially proportional to the measures assigned each string by the individual measures, right? It's very simple. Once you do that, you realize, after some thought, is that this operation is commutative, closed, has a unique inverse, has a unique identity. So essentially, this space of measures is an abelian group. So that's nice. That's really nice. Because since these things go down here, and as I said, minimal realizations are unique, that means that we can take this abelian structure and lift it to the space of PFSAs. Well, it's quotient space under the factoring out the minimal. So you only identify with minimal realizations, but let's not worry about that. It means that the space of PFSAs actually has an abelian structure, independent of what each graph looks like. What does that mean? It means that you can add and subtract PFSAs, these logical machines, probabilistic logical machines like integers. So you can give in two PFSAs, you can add them, you can subtract them, and that comes up, that induces this interesting question. So what if when I subtract G from G, what is a zero machine? So it turns out if you go through this calculation, it's not definition. If you go through this calculation and figure out what the zero of the abelian group is in the space of PFSAs, it turns out it's a coin. It's a fair coin. It's a Bernoulli half process for binary alphabet. It's a flat white noise, essentially. And for higher alphabets, it's still essentially a coin, n-sided coin. So with three-letter alphabet, it's a single-state PFSA with equiprobable symbols, symbols coming out of it. So that's a zero. And it's a zero. You can think of it why it's called a zero machine in multiple ways. Of course, it's a zero of the abelian group. Also, it encodes zero information because no matter how much you observe, the next symbol probabilities cannot improve or change. So it doesn't encode zero information, has a maximum entropy rate, Bernoulli, and one like uniform process and so on. Not uniform process. For a binary alphabet, Bernoulli half process. Yeah. So now we can actually go back and define our anti-streams in a more rigorous sense. So given a sequence S, of course, we're assuming ergodicity and stationarity. Then there is, and if it has a finite number of states, then there is a PFSA G generating the stream. The space of PFSAs is an abelian group. Go to the inverse, and there's a generative model to generate data from it. And that data stream qualifies as an anti-stream, is an anti-stream of S1. It's non-unique, but that's a rigorous definition. Right.
With some distributed probability. So how do you define the inverse of one particular sequence?
So yeah, so the reason why it has this family thing is because any particular model can generate many different sequences. Just like if you take a coin and you generate and you toss it 100 times.
The inverse of the process, not the inverse of the sequence.
Right. Yes. So any, but the set of sequences, as the length goes to infinity, becomes disjoint, of course, for any finite sequence. Pardon? Yes, ergodicity and stationarity. And there's also actually a weak mixing property that needs to be there. That's equivalent to having the finite number of states. Right. Right, right. So ergodicity, stationarity, and any of the mixing beta phi would suffice. Essentially, it means that the mixing thing is necessary because of having a finite number of states. If it's an infinite number of states, then you necessarily would need an infinite sequence to explore the state space, so in that sense. So the data smashing thing is interesting because, of course, you can take two machines and add them because they're in an abelian group, and if this one is minus the other, then it'll get 0. But the data smashing algorithm is interesting because it comes up with a way of avoiding constructing these machines. You can do this operation in the space with sequences themselves. You can take a sequence, invert it, add it, and see if the resultant sequence is flat white noise. So essentially, you can carry out this operation in sequence space itself. In the limit, it kind of converges in a limit, but you can approximately do that with finite streams. So that's the idea. And to just make sure that you don't think that its inverses are still kind of trivial, this is an example on a 4-letter alphabet. This is a signal. This is an excerpt of an anti-stream as computed by the data smashing algorithm. And this is flat white noise. So by looking at it, it won't be obvious. Yeah, I will in a moment after I talk about. Although I will not go through why. I mean, it'll seem very surprising that that actually works. And to actually know why that converges to an anti-stream. Yes, OK. We'll come to that. Let's show you some examples first. Brain waves. These are actual brain waves from a public data set from about 400 different people. There are 3 different phenotypes in them, normal or pathology, and normal with eyes open, normal with eyes closed. And if you compare this thing, eyes open and with epilepsy, it may look quite similar. It's kind of not easy to visually see it and say that this one is that. The classical method is to kind of model them with this complex stochastic models and fit data to it, find those parameters, and so on. What we did was simply take pairwise data streams, smash them, find this kind of smash distance. That gives you a 400 by 400 distance matrix, and these clusters kind of jump out of it. It's kind of very trivial once you come up to that point. And more importantly, or as importantly, when you take this distance matrix and look at the Euclidean embedding, it's a high-dimensional space, but if you look at a three-dimensional projection of the Euclidean embedding, you see that the data points kind of line themselves up in a curve. It's a one-dimensional curve. So that kind of, I think, shows that there's a one-dimensional order parameter space which it identifies based on the data. And that's kind of very intriguing, I think, to physicists. So another example, cardiac pathology. Again, this is actual data from people with normal rhythms and murmurs. And this is a kind of very hard machine learning problem. The accuracy, state-of-the-art accuracy, is about 68%. Before we went into it, and the accuracy for the data smashing algorithm for this application is, I think, about 75 or something. I have to look that up in the paper. Again, this kind of interesting and hard problem. Why is it hard? Because to do this in the classical sense, where you want templates specifying whether your heart is having a normal rhythm or a murmur, you have to have templates for these things. And the issue with that is no two persons' heartbeats are actually, it's very hard to come up with a template. This is normal, and this is a murmur. Or this wiggle things are murmurs. It's very hard. For doctors, yeah, it's kind of, they can just hear it and figure it out, but it's very hard to solve this machine learning problem, come up with these templates. But no, this is just a recording from. Oh, there's a quantization thing. I didn't write down what the quantization here was used here. You can look at that in the paper. Yeah, I didn't use any quantization on that for this thing. It was collected at, I think, 128 kilohertz or something, like a normal.
The problem is that, my heart can beat faster or slower, and you don't want to take that as big a difference. You want to normalize time somehow.
Well, we didn't need to do that. Maybe in different problems we would need to, but in this case we didn't need to do that. We just took every data point as it comes in. So it was recorded with an automated stethoscope, which directly produces audio signals. So we just kept the sampling rate same for each data stream. That's all we did. And if you have more data than you require, what would happen? A couple of things that can happen. That's a very interesting question. That kind of goes into technical things. What happens if you really have a simple signal and you sample it at like 1 terahertz? What would happen is that you'll have very long sequences of the same symbol. And that will actually screw up the algorithm if you really ramp up the rate and there's no information. This is incredibly long sequences of the same symbol would screw up the algorithm. But it's kind of quite robust. So unless you do that really badly, it's OK. But yeah, if you have this, situations like that, then we have to take care of that.
How did you come about the threshold for your conversion to symbol?
That's an interesting question, too. So you can obviously produce. So let's couple of things. One, there are obviously bad ways of doing the quantization. For example, I say everything below this is 0, everything below alpha is 1. Then we have a sequence of all 1s. That doesn't do us anything. So there are bad ways of doing it. And there can be multiple good ways of doing it. So how do we come up with a good way? So one of the things is we can start with this maximum entropy partitioning. So suppose you choose a binary alphabet. You kind of draw a line or split the range so that you have equal number of points on two sides. You can go for trinary, 4-alphabet, 4-letter, 5-letter, and so on. And then you see, and I'll come to that in a moment, you can compute something called a self-annihilation error, which is essentially you smash a data stream against itself, and that gives you an idea, if that is small, that it means you have enough data. So you see where, essentially, at what alphabet size you have the smallest self-annihilation error across the data set. And that's kind of a good way of choosing the alphabet size. If you go through the paper in a supplementary that I described quite clearly. So in this case, going forward, we get, again, do the same thing, pair by pairwise distance matrix. You find clusters and orders itself very nicely. Again, it's not a curve this time, but still a low order thing. Remember, it has like 60, so it's like the naive embedding is 60-dimensional in essentially a surface. So that's pretty nice. And they get about like 72, 75%, I forget, accuracy, which is significantly better than you get in the other state-of-the-art. The rest of the approaches, template-based approaches. So biometric authentication, here we're not trying to find pathologies, we're trying to use brain waves as kind of a fingerprint. And in this case, this is not, again, not a very hard problem, unlike the Hartberg thing. Using conventional machine learning, this works like 96, 97% of the time. Well, by using data smashing, it works perfectly. There are no errors. So the 122 subjects, they have recorded exemplars for them, and then you come up and record again, and essentially have to identify the person. At the same time, when you're doing that, you're being shown pictures, and you're trying to match pictures, 2 different pictures or something like that, some task, a visual recall task you are doing. Now, there are like 64 electrodes, and it turns out when we look at which electrodes are the most discriminative, most useful to do this, this data smashing thing, they are mostly in this region, which it turns out is the parietal lobe, which should be most relevant when you're doing this visual recall task, as domain experts tell me. Don't quote me on that. But that's what it does. And it's kind of finds, not only does this perfectly, but it finds the region of the brain which should be, in the current domain understanding, be most relevant in the task they're doing. So another example, differentiating between variable stars. You have Cepheids, RRL. You probably know this much better than me, so don't ask me what these are. I have no idea. Essentially, we look at photometry data, and the photometry is different for these different types of variable stars, which indicates different types of physics. Generally, what is done is that you have to know or somehow estimate the period of this variation as a kind of rotate or something. And based on that, you do folding and then use templates to match those objects. We didn't do that. We just took the raw photometry, did the smash matrix, did very good classification. I think this is the Ogle data set. I think the classical classification accuracy is about 98 or 99%. We get like 97 or 96%. So slightly worse than what you get with explicit templates, but I think it's pretty good. So as I was saying, an important feature of this, the whole data smashing idea, is this notion of self-annihilation error. So what happens if you smash sequence against itself? So you're doing S minus S, essentially. So it should be 0. You should get flat white noise always. Well, no, because you are doing all these manipulations, the inversion and addition, so you're doing some stuff in this box, which means that it's not always 0. It will be 0 if you have enough data so that it explores the state space. So that means that gives us a way of figuring out whether you have enough data, particularly when you smash it against itself, the diagonal of the distance matrix. If that is small enough, then you have enough data. If that is not small enough, you don't have enough data. So that is pretty nice, right? Because if you, at the end of the day, somebody has to come in and tell you how much data is actually enough, then it kind of misses the whole point. Then it's the whole idea of doing things without features kind of goes out of the window. But you don't, because you can look at the self-annihilation error, and if it's small enough, then you know you have enough data. And it's also used for finding partitions or quantizations. There's one more example. I was not sure whether I want to talk about it. So essentially, as you type in your keyboard, the time delays between the key presses. The question is that, can that be used to recognize who the user is? And the answer is actually yes. And we did some simple experiments, not too many, with grad students in our lab who collected data, and does actually work. The more interestingly, this was actually done as a DARPA proposal, and they said it's great, and then didn't fund us. But it's kind of, the idea is this, that you have these exemplars saved in the memory of the computer. You come in and say that you are this user. It pulls up your corresponding exemplar and starts smashing as you are typing. And when the self-annihilation error drops below a threshold, your smashing distance should also drop below that threshold. If it doesn't, if it's like this remains higher, self-annihilation error drops, then you have enough data to make a decision, and it's not you. So you get bumped. Not only that, you can do this kind of continuous authentication, continuous cognitive fingerprinting-based authentication. Is that suppose you ask or you get somebody to give up their password and start using their computer, then what would happen? First, the actual user was using it. So both the self-annihilation error and the smash distance falls below a threshold. Then there's a user change. Everything goes up, spikes up, and then you have enough data again that falls, so self-annihilation error, but you're not the same user, so you get rejected. So it seems a pretty cool idea. Didn't get funded. We can also use this. So up to now, I've been talking about time series, so single stream of data. Can we use it for multidimensional data sets, like images, for example? And the answer is yes. Recognition of handwritten digits. 4 and 9 is particularly difficult. It's understood that they're kind of difficult for handwritten thing because most people actually don't have a very good handwriting. And the way it's generally done is to, again, manually pick those features, optimize them, and it works pretty well. It works with like 99.6% accuracy or something. It's pretty good. It's very hard to beat that. However, can we do something different where we don't have to go in and find these crazy features? And the answer is yes. What we do is essentially do a random walk on each character, which produces a stream. When it hits white, you produce a 1. When it's black, you produce a 0, or the other way around. It doesn't matter. Once you do that, you get streams. You smash them. And how well does it work? Well, quite well, actually. This is a 4 and 9. It doesn't get up to 99.6. It gets up to like 97%, which would be terrible if you had used features. 97% was the state of the art like 6 years back or 7 years back. But here you're doing the same exact algorithm and without actually using any features. And again, when you look at the embedding, there is a one-dimensional embedding of it. So if you ask me why this one-dimensional structure shows up from time to time, I don't know. Maybe it's just the problem. Maybe it's just the order parameter of the particular problem. That's kind of very interesting, which I'm still thinking about. So now let's talk about what has exactly been done. And as I said, I'm not going to take you through the math to prove that the steps actually work, but this is what is done. So you want to first find an anti-stream of a given sequence S1. So suppose the quantization alphabet has 3 letters, because binary is kind of trivial. So what do you do? So for a 3-letter alphabet, you need 2 copies of it. And by copy, I mean it's an independent realization from some underlying process. So how do I create a copy? Well, essentially, you write down the first stream, and you generate a stream from flat white noise. And if they do not match, you do not write anything in the output. So the first one is 2 in S1, and in the flat white noise that you're generating, it's 0. They do not match, so don't write anything. If it matches, you write 1. If you write down the thing that matches. 2, again, matches, so you write down 2. Doesn't match, don't write down anything. If you keep doing that, you can show that this, in the limit, essentially becomes actually an isometric function, but let's not worry about that. This becomes an independent realization from the same underlying process. And you need 2 of them, because they're 3-letter alphabet. So 1 minus the number, or the cardinality of the alphabet. Once you do that, that's your 2 copies. You have got 2 copies now. And you want to generate an inverse. Well, 3-letter alphabet and 2 copies you have got. You line them up, and if they do not match, then there is 1 more alphabet symbol that is still there, only 1, so you write that down. And if it matches, so 1, 2, write 0, 2, 0, write 1. If it matches, do not write anything. If any 2 matches, do not write anything. So if you do that, again, you can show that this, in the limit, essentially becomes an anti-stream of the original stream. So you see intuitively why this works. A very rough thing. It's actually kind of hard to describe, give an intuitive explanation. But what you're trying to do is kind of balance a number of 0s, 1s, and 2s so that's what's happening. Because when they add up, they're supposed to produce flat white noise where everything is balanced. That's the definition of flat white noise. So that's the anti-stream. And then you take the other stream, S2, and do the same thing as you did with the copy. When they match, you write it. And they don't match, you don't write it. And that's your output. And essentially, you have to take this output and check whether that's flat white noise. And what you note here is these are pretty long streams, and the output is really tiny. It's 4 letters. We can't really say that's white noise or not. So that's the cost you're paying. This output data rate is smaller, often significantly smaller, than the amount of data stream, length of data stream you're putting in. So that's a cost you're paying by not using models. That's the direct cost. So you need quite a bit of data here to essentially have this result long enough to make the determination whether you have flat white noise. And the uncertainty of the result also is a function of this. Because if this was infinite, you could do this with almost like 100% accuracy. But you can't, because if you have finite stream, this one is finite, much smaller than this one. So how sure are you that this is actually flat white noise when you say it's a flat white noise? Or not, how sure you are then? So that way you can compute uncertainty values on there. Do you have any questions on this? No, this one, last one. Yeah.
How quickly does your data set have to grow as a function of the alphabet?
Exponentially.
Right? I mean,
It's exponentially. That's the only thing that I'm not happy about. There's no way around it. But there's no way around it. You cannot do it. You cannot do any better. The reason is because your state space explodes exponentially with alphabet size. When you think of it in a discrete way. So there's no way. There's no magic going on. You have to explore the whole state space. So it's like, think of a two-dimensional space. How many squares can you draw if you define the size of the squares? Now, if you say three-dimensional space, how many squares can you draw? 4 dimensions, exactly like that. Yes, you're asking something. But you can actually specify that question, what is the exact relationship of so basically this ratio of this length to the initial length is defined as annihilation efficiency. And you can write down analytically what is the functional relationship of how does an annihilation efficiency scale with alphabet size, with all these things. So
what's the largest number of servers using?
27. But that was a really, really long data. Essentially, we're treating text from different entire work of Shakespeare and all that. So yeah, it's the most. Oh, no, that's the quick answer. The one thing that brings up different, which I should probably explain, is that synchronization between these two streams are not important. Again, that is because of ergodicity and stationarity. So it doesn't matter if you switch, if you shift the start points, nothing would matter. That ergodicity, that's why. Right, it's not, because what you're finding the distance between the underlying models, right, is not actually a distance between the data streams. It's actually using data streams. What you're trying to get at the distance between the underlying models, where it doesn't really make sense. This model is out of phase from that model is not a sensible statement. When it produces data, you can say one is out of phase with another, right? Like a sine curve generator is. Right, exactly. So I asked what your questions is because that's kind of ends data smashing, and we'll talk about other things. Like, so all this time you're saying, okay, there is this probabilistic automata, we're not going to find it, we're going to find distances doing data smashing and all that. But that's kind of a difference between classification, pattern classification, and pattern identification, right? What if you really wanted to know the model? Can we know the model? Yes, we can. We need more data. It's a harder problem than just doing data smashing. It's more efficient, not harder in the sense of the math. It's more efficient to do data smashing if you're only interested in the distance between the models. If you define the models themselves, it's harder. That's understandable. So PFSA is a little bit about the semantics. Well, they have states and alphabets, labeling the arcs, and also have transition probabilities. That's pretty much it. So essentially, we're saying if you have data stream like this, we want to find a generative model that models the data. Now, one thing, whenever I talk about this, no matter how many times I state this, somehow this notion comes up in people's minds that Q1 is somehow 0 here, and Q2 is 1 here. That's not it. The states are not the alphabet symbols. If you remember what I talked about in the construction, states are equivalence classes of symbols. So they're not the symbols themselves. So what does it mean? Suppose this is actually a correct model, in whatever philosophical sense you want to define correct, of this data stream, then what does it mean? It means, or more specifically, what does it mean to have two states in the model? What it means is the following, that there are only two contexts that you can be in the data. Either you are in state Q2, or the one context, where the next symbol probabilities are 10% and 90%, that's a distribution. Or you can be in the other context, where it is 70% and 30%, and there are only two such contexts. That's what it means by saying the two causal states in the data. So it's something intrinsic. You cannot represent it by a single state, because that's the minimal model that it can have. Of course, you can have non-minimal realizations of it. So when we say we want to go from here to here, we want to, yeah, that's what I just said. We want to go from here to here. What I mean is that I do not specify the model structure or the transition probability. I just have the data. I want to go from here and find everything that is there. There's a 2-state model, 3-state model, 25-state model. We want to find that. So how does that work? How do we do that? Well, it's kind of very simple. We use this notion of symbolic derivative. So we ask that given that you observed some symbol fragment, sequence fragment, what is the probability of seeing 1 next or 0 next for a 2-letter alphabet? For higher number quantization, you have to fill that up. So that's what I call the symbolic derivative of that sequence. So phi s omega s is the data that you have. How do you find it? Well, it's very simple. You go and look for that particular sequence, see how many times 1 happened after that, 0 happened after that, and normalize. It can't be simpler. If you have enough data, if things are guarded and stationary, that will converge and will give you essentially phi s omega. Right? If you had the PFSA, you could compute it analytically too, but this is a way of estimating that. And you can show that it converges rather rigorously with measured theoretic machinery that works if you have ergodicity and stationarity. So how do we use that to actually find the model? Well, you compute all this symbolic derivatives. OK, one question. So here it is phi s omega, phi s 1100. I showed how I computed that. What do you think the phi s empty string is? What happens if this omega is empty? What do you think that is? So I just described how I compute phi s omega, right? Well, omega is 1100. You look for 1100 everywhere in the stream, see what happened after that, how many zeros, how many ones, and normalized. So what is the symbolic derivative of the empty string? What is phi s lambda? Yes, exactly. So that's the frequency of 0 and 1, because then it matches 1100 matches wherever 1100 is. If omega is empty string, it matches everywhere. So it's the frequency of 0 and 1. So that's the lambda. That's the empty string. Symbolic derivative is this, and you can compute all of that. The way the algorithm, the genesis, is actually I'm describing the algorithm genesis. The way it works is the following. You start with a single state, label it with the empty string, and see what its symbolic derivative is. And then you ask, what is the symbolic derivative at 0, or lambda 0, which is 0. And you see it is different from that of the lambda. So you produce a new state, mark it with 0, because that's how you got there. Then you ask, what is the symbolic derivative at 1? You see it's again different, 0.9 or something from both of these. Produce a new state. Then you ask, what is the symbolic derivative at 0 from here? So process this state next. And you see with 0, you get the same symbolic derivative. See, 0, 0 is green again, same as 0. And 1, 0, 1 is red, which is close to the 1 thing. And you do this and you get that. And then you remove things which are outside the strong component. Those things fall off, and essentially you get this model, and then you just take the data, choose any state, run it through it, count the number of times each arc is traversed, and normalize, and that will give you the probabilities. Again, ergodicity probability doesn't matter where you start from. So you see, you just found the state, correct state structure, and correct probabilities from the data without assuming anything. So one thing to note here is that when I say these things match, they don't match exactly. There are small differences. So there's a resolution parameter somewhere. So if you change that, the model will change. So I don't like that. Can we fix that? Well, yes. You can use data smashing. We can take data, use this particular algorithm, which is called genesis, and find this model. This is a generative model. We can generate data from it. And if it's a function of particular resolution, if you get a family of models, then you get a family of such data streams. You smash it against the original stream and see which one minimizes the smash error. So that's your optimizer's takes out the resolution parameter and gives you the best model you can find. Well, you have to choose a range of the parameter anyway. So that's how you can come from data to model without assuming structure. Now, it's a pack efficient and all that. I'm not going to go into that. You can take a look at the paper. The point is that you have different data streams with different statistical complexities, and it will find those itself. There are some variations of this algorithm, the same idea that you can find PFSAs from data done by Crutchfield, by Shalizi, and others. So the whole idea, at least at a philosophical level, I didn't come up with it. But all those previous algorithms had restrictions on what kind of systems they apply to. And that is not true for Genesis. Anything that has a probabilistic finite structure can be inferred by Genesis. So what can we do with it? For example, well, a lot of things. You can find models. That's what it does. For example, you can take history of earthquakes in California, which looked something like this for the last 30 years at a weekly resolution, so 1 point every week. And you can take that and can quantize it in some sense here, and there's a way of choosing good quantizations. In this case, magnitude 4 or below is 0, above is 1. So that's like a binary quantization. You have this binary sequence encoding the history of earthquakes in Southern California. And you can take that and use Genesis and find a model. It's a very simple model, as seismologists are not very happy that it was such a simple model. But you can actually use that to verify some of the empirical laws that are known in that field. For example, the Omori-Utsu law. Again, I really know very little about it, but essentially what it says is if the frequency of earthquakes goes up as you approach a large event and goes down as you go away from a large event. So it goes up, have a large event, then it goes down. And using even this very simple model, you can actually see that those things happen. You can see those decays in the frequency. And not only that, the coefficients of the decay that you compute from the model matches up almost exactly, which is very surprising to me, with what has been calculated by experts from catalogs. These are all other papers which are published in the in the domain. So that's very nice. But that is not really good, not really that interesting. Okay, you have a simple model that you can verify laws that were already known. What would be great if we could actually predict earthquakes? Now, that you really can't do that well with those only Genesis, only those models. What you need to do is actually take account of what is happening in other parts of the world. You have to see what's happening in Japan, how that affects what's happening in California. Because remember, it's actually a giant plate which is moving around. So you have to kind of take advantage of these other data streams and how these cross dependencies work. So you have to somehow address that. On similar lines, another problem that is almost identical, at least at the level of abstraction that I'm talking about, is this influenza dynamics, right? Epidemiological dynamics. So we have this huge data set at IGSB in Chicago, where you have incidence data for last 470 weeks, which is like about 9 years, the temporal resolution of week and spatial resolution of US counties of many different phenotypes of diseases. And one of the phenotypes is influenza. So it has like data from about 150 million patients, and when you kind of see it, visualize it as a video, as a movie, you would see that you would see this kind of infection waves being generated at different parts of the country, moving across. You see this kind of clockwork precision at which the flu season comes back every year. So there's lots of different patterns. Now, if you take one county, then that is a time series for 9 years. Now, can we predict it, or can we make find patterns that are useful in some sense from it? Again, if you have multiple counties interacting, if you can find these cross dependencies, that becomes really, really important. So here, it's kind of going into this notion of finding causal dependencies between data. And finding causality sometimes is kind of obvious what's going to happen. Sometimes it's not. For example, if you look at incidence data of how changes in incidence when two neighboring counties in Alabama, it's kind of obvious that there are correlations, right? What is not obvious is whether there is causation. And how do we define, how do you even go towards mathematically thinking about what causation is? Well, a couple of ways of doing it, a couple of established techniques. One is the Granger sense. I'm going to talk about that in a moment. One is Pearl's sense. I like Granger's sense better because it's like a more statistical approach to things. And essentially, the definition of Granger causality in its basic form is the following. It says that y, a variable, is a cause of x if y has unique information that helps you to predict x better. That's it, very simple. Even with that simple definition, a couple of things happen. You can rule out certain cases that is saying that there's no causality or Granger causality. For example, if x is a sine wave, then no matter what y is, y has no Granger causal influence on x because x can predict itself perfectly. Y cannot improve it. Similarly, if they are just scale shifted, not y shifted, not x shift, time shifted, but the scale shifted on the magnitude direction, then also there is no causal influence because one can predict itself as well as the other can. So there's no causation in those cases. So to just rephrase the definition in mathematical terms, essentially what you're saying is that we need to verify that this inequality, that the future distribution of the future values of x, given all past of x and all past of y, conditioned on that, whether it's different if you only condition on x. And if they're different, then y has some specific information that changes this future distribution of x, and that is the Granger causal influence. I keep saying Granger causal influence because whenever I say just causality, that becomes a lot of problems with it. The thing to note here is that whenever you say xn plus 1 condition in all past values of x, what you're talking about is actually model inference, because that's essentially, to know that, you use a model. Now, if you use a simpler model, if you use a linear regressive model, then you'll get causality in the mean, Granger causality in the mean. If you use a more general model, you'll get a more general thing. Now, can we use a non-parametric inference, not specify what models we are going to use or what assumptions we're going to take, and still essentially carry this out? Well, there's maybe a couple of ways of doing that. One of the ways I'm going to talk about is to use a generalization of inferring PFSAs, where we infer this kind of dependencies between data streams. I call them, the models in that case that come out, I call them as cross PFSAs. So there's slightly difference syntactically. Here you had arcs, symbols, probabilities. Here you also have arcs, symbols, but no probabilities. But there's output distribution from each state. The idea is that here you have the transition probabilities because you're modeling a stream, and that specifies a transition from state to state. Here you're saying that if the first stream is in state Q1, what is the symbols that I expect to see in the other stream? So there's an output distribution at each state. So essentially, earlier we went from data to model. Now we want to go from data, I want to predict the next symbol in our stream. And in this case, they are synchronized. So in this case, we had a PFSA. In this case, I call it X genesis, X is cross genesis. It will get a cross PFSA. How do you do it? Again, it's almost identical. We'll use symbolic cross derivatives, phi omega S1 to S2. This is S1, this is S2. If you have 1, 1, 0, 0, look for 1, 1, 0, 0, and see what happens after that in the other stream. Count it, normalize it, and if you have enough data, it will converge. And if you have ergodic stationarity, ergodicity and stationarity. So one of the things that we can do is to compress this degree of causal dependence into one number. It's called the coefficient of causality. It's actually an information theoretic definition. So it says that gamma A to B, so stream A to stream B, is essentially the decrease in uncertainty in predicting the next symbols in B when you make observations in A. Essentially, that's what it means, the relative change in uncertainty. So the expected change in entropy of the next symbol in HB, the other stream, due to observations in HA over the entropy of the next symbol distribution in HB when you make no observations in HA. And the definition, as if you write it down in terms of symbolic derivatives, is essentially this: excitation over all streams in sigma star A. So sigma A is the alphabet of the first stream. Phi x HA to HB, symbolic derivative, Shannon entropy, and here no observations, so lambda, right? And 1 minus. So how do I compute that? Well, phi x HA HB comes from the construction. Phi lambda HA HB also comes from the construction. H is Shannon entropy. The only problem, it seems, is taking an expectation over a countable set, and that's slightly problematic. The way we do that is we figure out, so basically we're identifying something like this, which is an XPFSA, right? We want to know at what frequency does these states occur in the first data stream. Because then if you know that you're in Q1, Q0, you know in the second stream, these three symbols occur with this distribution. So we kind of have to know at what relative frequency these states occur in the first data stream. If we could know that, then it would be obvious in a moment that we don't really have to take an expectation of the countable set. Well, how do we do that? I'll skip some details. Essentially do something like this. You take the XPFSA you've identified, you drop the output distribution, you get a graph labeled with symbols. Then you take the first data stream, cycle it through the thing, and see how many times each edge is traversed. You normalize that. You get probabilities, something that looks like a PFSA, syntactically identical to a PFSA. Find the Markov chain from it and compute the stationary distribution of the states, and that's what gives you a stationary distribution on the XPFSA. If you don't, this is not obvious what I just said, don't worry about that. The important thing is you had this expectation over sigma star A, and you can replace it, because of what I just said, with a sum, a finite sum of all the states of this projected machine weighted with the stationary probabilities. And this is the same thing, because remember, at the beginning of the talk, I talked about this equivalence relation of which determines what the states are. So once you do that, this can be computed, this can be computed, this can be computed, and you can compute gamma. Note that this is asymmetric. So for two streams, gamma AB is very rarely equal to gamma BA. You have to actually jump through hoops to come up with a system where they're actually equal. And they're all back efficient. So one of the things to note before we go forward is that you can compute. So I say that in cross-genesis, you're finding models from one stream to the other. How does one stream influence the other stream? Now you can ask whether the influence occurs at step 1 in future, step 2 in future, step 3 in future. So you can find different models at different time shifts. Also, instead of using a second stream, you can actually ask the same thing about a time-shifted version of the same stream, right? So you can also do the same thing, run this particular algorithm, when you're using or looking at time-shifted versions of the same stream. So I call them self-models. This one's cross-models. So you're right. This can also be done with genesis. So at that point, the cross-genesis, X-genesis becomes like a generalized version of genesis. So what can we do with them? Before we go that, if we find this gamma between time-shifted versions of the same stream, what does that remind you of? That reminds you of essentially autocorrelation. So if you take this kind of nonlinear process, say noisy Duffing oscillator for some values, not important what the values of the parameters are, and you take the two streams as xt and xt plus delta, and find gamma as a function of delta, it decays kind of, well, noisy monotonicity with time, with a time shift. That's what we expect. That's what should happen when you try to predict things in the future. So what can we do? And also note that whenever you're computing gamma, that's a function of the model. So you are actually finding those generative models, cross PFSAs, for every time you're finding gamma. And you can find a gamma between two streams. You can find a gamma for different time shifts. So you have lots and lots of models, generative models that are coming up, which are predicting things between A to B or A to B with some time delay, some different time delay. So for that earthquake problem, you find literally thousands of models. And we can use them to predict what's going to happen. If you can fuse those models, fuse their predictions, we can come up with quite good predictions of what's going to happen years from now. And how does the prediction work? Well, again, not really important, just to make sure I cover everything. You have an XPFSA. You have the data stream for the first stream. You take a short history, use that to find the current distribution of states in that model. It's very similar to what I did before. And once you have a distribution of the two states, if you are, say, if you're in Q0, you know the output distribution for the other stream is this. Q1 is this. If you have a distribution, well, you just combine them, weight them. And that's a prediction using only one cross model. If you have multiple cross models predicting the same stream, you combine them essentially by weighting with the coefficients of causality, with the gammas. And note if the gamma is 0, the fusion weight becomes 0, and it falls off. Now this, of course, is kind of empirical, because the rest of it is really no other way of doing it, whereas the fusion, well, there can be other ways of doing the fusion, too. But this one works pretty well. So essentially, this is the idea. You have data coming in, and you have what I'm trying to get at is a non-parametric, non-linear, universal predictor. And what is inside is X-genesis and data smashing. You need X-genesis to find the models. You need data smashing. We take out the dependence on the resolution parameters. And you also can get coefficients of causality, the exact models, and so on. But the idea is that essentially it's a non-parametric, non-linear predictor. And even if you don't worry about what's going on inside, essentially you can treat it as a black box. It's called SciNet. I like acronyms. It's a causality network. And it uses this concept of Granger causality, formal languages, what I was just describing for the last 1 hour, ergodic theory, abelian groups, and so on. So how well does it work? Because that's important. So going back to our data, of this incidence data that we have on different diseases, what we can do, since we have county-specific data, we have these different time streams, you can find this causality coefficients between two counties. Say you pick a county, find all its neighbors, find the causality coefficients, you'll get a picture like this. If you draw a line, a vector proportional to the causality coefficient you found from the center of the county to the geographical center of the neighboring counties, you'll get something like this in each county. You find the resultant vector by just doing a resultant calculation, and you'll get something like this. So for different diseases, you get this different causality field. For HIV, you get something like this, and you can see we haven't explored. This is a very new result. We haven't explored what each of these different pictures mean. But we can see some associations which suggest that we're getting something very useful. In this case, you see everything converging on population centers, which may be true for HIV because the humans are the only vectors. E. coli, fungal infections, and you can kind of stitch those arrows, the vectors together to get a streamline, to get streamlines. And again, you see things converging on the high population centers. I'm not going to spend too much time on that, except, yeah, staph infections, yes. So this is kind of interesting because you see there seems to be staph infections. Causality field begins here, goes to sometimes the population centers. In fact, always goes to the population centers. But you see there's a kind of a source that seems to run through here. Do you know what that is? That's actually Mississippi. And there's been some anecdotal evidence that if you are around Mississippi, particularly in Mississippi, then your chances of getting staph infections goes up. Very anecdotal evidence, very hard to justify it, because this is not something that is an actual, well, there has to be a mechanistic ground truth to it, but this effect could be, or probably is, purely statistical. So it's very hard to justify this by actually doing anything else other than this kind of techniques. So this is not like, I'm not saying this is true. It's kind of, yeah, so a lot of things that we've done. I have not done them yet. Very new results, very new results. But for the staph infections, even in here, there are actually rivers. I forget what the name of that river is. But there's other branch here. Yeah, could be, could be. So it's just, the influenza, the thing is much more complete because that's we are almost ready to submit it. So if you look at the prevalence of influenza, I showed you the movie before, but if you normalize it with population, you get the prevalence, which seems to be more prevalent in the south and southeast. And that's kind of interesting because then it couldn't be just population. Influenza is better vectored in cold weather, not that cold. Population could be a factor, but there's high population here, 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 here. Seems to be something specific about this area, which is kind of confusing if you think about that why, or try to reason why there should be high prevalence of influenza there. Well, we did this causality field, and that's what the field turns out to be. And when you look at where the sinks are of those causality streamlines, they're mostly here and here. Again, does this prove that this is this kind of shows that does it actually rise to the level of a mechanistic explanation? I don't know. That's more like a philosophical question. But this is what you see in prevalence. It's hard to explain using other factors. I did do the calculation. And it seems the causality streamline, so infection starting here somehow has causal dependent, like causally affects things along the streamlines. And the streamlines go and sink most of the time in those areas where you can see this, the gray things are the prevalence maps, and they kind of match up almost perfectly. So is that a causal explanation? I don't know. That's, again, a philosophical question.
You get this model, what predictive value it has?
Yes.
How do you validate it?
Good that you asked that. This is what we get. So since we had all these models, and the 3,120 counties, The algorithm also tells you what is the kind of average value of a good delay time shift. In this influenza, it's about like 2 to 3 weeks. So I took about 6 weeks, right? So 3,000 models, 6 weeks. So you have that many models, right? And each county has about like 6 or 7 neighbors. So you end up with, say, 5 neighbors, 3,000 counties, 15,000 into 6, about 90,000 models total. So not all models have gamma greater than 0. So ones which have gamma greater than 0 are about 50,000, 49,000 actually. So we take those 49,000 models and we fuse their predictions, as I did before. Well, for each county, it's only like about 6 into 6, or 40 or say 50 models. So let's look at one particular county, and this is not the best county. It's like I chose one in random, but there are many counties like this. I'll show you in a moment. Collingwood, Texas, and if you want to predict what would be the upticks, remember it's a binary alphabet, so change in incidence is going up or going down. 1 week ahead, so that's the ROC area you get. So ROC is a receiver operating characteristic, very commonly used in machine learning. It's the relationship between false positives and true positives, right? And in the best case, it would be this. It will have an area completely covered. And it's not that. It has a 95% area. So that's the performance. As you want to predict further and further into the future, it worsens, as expected, 86%, 80%. And this is pretty good. If you can predict influenza upticks with the ROC area of 95%, that's a result that is not really there anywhere else in the literature. Los Alamos is actually trying to do this, predict influenza things. And I have some result. Well, one can argue it's a quantized result, just upticks, not exact values. But yeah, well, I don't think there's an analog of that itself. So what happens when you predict for all counties? What is the distribution of the ROC areas? Well, 1 week, 2 weeks, 3 weeks. So you see there's lots of things above 80%, 95%. Slightly moves this way, slightly moves. So that we expect that. And you see 1 week is average ROC area over all 3,000 counties is 80%, 78%, 75%. That's what it looks like. 1 week prediction horizon, the ROC areas, blue is great, then cyan, then green. You see most of it is pretty good. 2 weeks, slightly worsens, 3 weeks worsens, but it's pretty good still. So that's what you get. That's the prediction performance you get. Do you have any questions on that?
Have you tried to use other than neighboring counties where you know there is much traffic between?
Yes, that's one of the things that's there in the paper. So when people are moving around and they're tweeting, so they think if they've not enabled their Twitter location things, Twitter doesn't know where they are, but they do. And they shared that information with Microsoft. And Microsoft shared, well, some scrubbed version of that information with us. So we have as a social connectivity map as people are moving. And you see that that matches up quite well with the influenza patterns. So that becomes a confounder. Can that explain the influenza dynamics perfectly? And it turns out no. Well, there's also the question of whether aquatic birds cause it. So it kind of gets messy. This is the part which is nice and clean with algorithms and stuff, explaining all those things. We bring in these different kinds of factors like social movement, migration of birds, location of airports, all those things, and then combining them, it gets a little messy. Honestly, I would rather just stop here, but in the paper that's going out, it has all those things. I can send you a copy. So, yeah, figuring out distribution of birds as they move. And then at the end of the day, you can't really summarize the result as here's the ROC area, and here's the algorithm so that it works. Here's the proof that it converges. It's not like that. Because you can never be sure that these factors actually cause it. So that's anyway, so let's look at the earthquake results. So I talked about California, and so what happens if I try to predict what I just did for the influenza for earthquakes? Remember, again, it's quantized. The amount of data that we have good data. By we, I mean everybody. USGS has good data from about 78 or 79 up till now. So the amount of data that we have is limits the degree of quantization that we can do. In this case, we only do about binary quantization to have good results, low uncertainty, and so on. So the quantization is at magnitude 4. So any earthquake under magnitude 4 mapped to 0, any event, and higher than that is mapped to 1. And the time quantization in this case is 1 week. So weekly quantization in time, magnitude quantization at magnitude 4. When you do that and you find which areas, which points kind of influence California the most, you see that they kind of line up like this. And note, this is done without any understanding of where earthquake-prone centers are, and essentially it just found the Pacific Ring of Fire. And then we do this prediction thing, and it turns out these areas are the most effectively predict California. And how will this do it? Well, if you just use self-model, self-history, you get about 88%. If you use the cross models, you push it up to 98%. So think about this, and the prediction horizon is 300 weeks. So think of this for a moment. It means that 300 weeks, about 6 years. Pick a week 6 years from now. I can tell you within that particular week, there will be an earthquake of magnitude 4 or above. Of course, the argument would be you just use previous data and you use ergodicity and stationarity. None of those could be true. So just because you came up with a model in the past doesn't mean it will hold true tomorrow. Yeah, but those, if you go by those arguments, then nothing, no science actually works. All science you have is essentially based on past data. Yes?
Have you done the same thing with higher magnitude?
No, so what happens when you,
6 or 7?
they're so rare. So what happens is, that's the issue that I was telling him, is that if you have very long sequences of one particular symbol, that's a problem. So it shouldn't be. If you have infinite data streams, that won't be a problem. It's because of the amount of data you have about 2,000 data points for each location. If you have 1,950 zeros, that really doesn't work.
How much better it is than if you did use all these numbers?
It's incredibly better. Because there are two reasons for that. People do not want to predict. So if you show this to seismologists, they'll not be very impressed. The reason is 4 plus is not something they're interested in predicting, because that is not really something that causes property damage. 4 is, yeah, we'll shake a bit.
No, I'm speaking something else. 88% is stamp model.
Right.
98% using everything.
Right.
At what level do you get to 98%? Do you need over 20 points or 30 points or whatever?
No, you actually get a lot. In fact, if you don't use self-models at all. So this is a very interesting question, and this I was talking to him before that. So it may sound, maybe I haven't done a very good job explaining this. I'm sure I haven't. It sounds like it's a black box, and it just comes, so results just come out of it. But that's not true. So this particular thing is only true for California. And as I told you, what models that push it to 98% you can identify. So you're already identifying this causality network of different points which kind of drives the seismic dynamics on the globe, right? So that 88% and the breakdown is for California. In other parts, it may be lower. Actually, it is lower. California is much easier to predict for some reason. And also, in this case, if you do not use self-models at all, you get 98%. If you use self-models, you get 88%. That's because I think my conclusion, or my understanding is that California is kind of a driven point. It's actually driven by other effects. So if you only use those effects, particularly from here, then that is much better, almost perfectly specifies what's going to happen at that quantization levels at prediction horizon. But if you take some other place, for example, if you take, I haven't actually done all the results. It takes some time to carry this out. It's still running, actually. But if you say try somewhere here, you do not get 98%. You get like barely 80%. And there, if you use cross models, it doesn't really help, because it may be one of the places which is generating the information. So all this structure is not a black box. It actually helps you to see what the internal influence structure is, which is connecting different points, how the dynamics relate to each other. So it's not a black box. That was the point of that statement. So other things that seismologists know is that since all this affects, when I say cross models affecting one another, essentially it's like a slow diffusion of stress. They call it post-seismic activity, or post-seismic dynamics, that is going through the Earth's crust. So it's a very slow process. So what is the memory of that? So there's an idea of what the memory is from the understanding of domain knowledge, and that should be around a decade or more than that, like time scale of decades. And we see that if it's restrict cross models to ones which have time shift at 200, 300, 400, 500, 600 points, it kind of levels off at around a decade. So that kind of matches up with what is known. So one more example I will quickly give before I end. That is essentially trying to model interaction dynamics in retroviruses, HIV, for example. It's a very simple example. So there's lots of sequences in the LANL database. So these are not time series. I want to know, and every position in HIV is variable. So I want to know whether mutations here have something to do with mutations somewhere else. Has to be because function has to be conserved. Now, how do we do that? These are all sequences of genomes of different viruses. So it we can't do a time series this way. We can't do a time series really this way because those can be shuffled. It doesn't make much sense. So what I did was something like this. Take a position I, define a neighborhood, and essentially string them together. And J, again, string them together. Of course, these actual rows can be interchanged, but these neighborhoods remain the same. So if you interchange the rows, since they're interchangeable, that introduces random variations because of this arbitrary indexing of the rows. But random variations should not have any non-random patterns, so that should cancel out. So the only thing that should matter is this patterns in the neighborhoods, whether they relate to neighborhoods here, another stream. So essentially, we generate all the streams for I and J, find the gammas, and it looks like this. Not very instructive. But we apply a standard modular detection algorithm, and it splits up into roughly 3 modules. And it turns out that this blue one is exactly GAG. The other one's roughly pol and roughly N. So think about this. You have this collection of genomes. You just applied a zero-knowledge algorithm, and it just told you that there are roughly 3 modules in that, and that corresponds to the 3 basic things. One of the basic things that is known about retroviruses. All retroviruses have GAG, pol, and N. So that's pretty interesting. So also in HIV, we know what each location corresponds to what gene. And since we have these gammas between different locations, I kind of looked at it at a coarser level to see what are the causal influences between the different genes. And here it's still a directed network. Here the directions are represented by clockwise arcs. And it turns out, when I look at that, I get this kind of network where integrase, reverse transcriptase, protease, VIF, VPR, P17, all these different genes are there for HIV. And then I looked at which interactions are known. There's a paper for that in PubMed, and which are known. So it turns out the gray ones are the ones which are known. So it is known that integrase interact with the reverse transcriptase, or protease, which cuts up everything, chops up everything, interacts with a lot of things. But then there's also some very strong interactions which are not known. For example, there's no reference why ribonuclease H will interact with integrase, or with why integrase will interact with VPU. There seem to be a different parts of the life cycle of the virus, but still there seems to be a strong causal association. So that may be actually known, results not known, and that comes back to this notion of hypothesis generation. You can go back and maybe people in the white coats can look into that. I don't know. So that's it. That's the last slide. It's essentially what I talked about, essentially a universal predictor. And using these notions of non-parametric inference, statistical causality, universal similarity,